Computer vision is a subdomain in artificial intelligence with a wide range of applications focusing on image processing and understanding. These tasks have a variety of real-world applications, from annotating images at scale, detecting abnormalities in medical images to extracting text from documents and generating text responses based on visual data. Traditionally addressed through convolutional neural networks, CNNs, this field has been revolutionized by the emergence of transformer architecture. In this video, we will explore 4 fundamental computer vision tasks addressed by transformer vision models. While transformers are well known for their applications in language processing, they can be effectively adapted to form the backbone of many vision models. Vision transformers leverage self-attention mechanism to allow image patches attend to each other. They have less inductive bias, meaning they are less constrained by specific model assumptions compared to CNNs, but consequently require significantly more training data to achieve strong performance on generalized tasks. Advancements in vision models have fueled interest in developing multimodal models that can process both image and text data simultaneously. Vision models focus on unidirectional transformation of image data to numerical representation and typically produce score-based output for classification or object detection, image classification and image segmentation task. Multimodal models, however, require bidirectional processing and integration between different data types. For example, an image-text multimodal model is capable of generating coherent text sequences from image input, image captioning and visual question answering task. We will provide an overview of state-of-the-art vision and multimodal models, such as ViLT, Vision Transformer, DETR, Detection Transformer, BLIP, Bootstrapping Language Image Pre-training, and ViLT, Vision Language Transformer, that specialize in various computer vision tasks including image classification, segmentation, image-to-text conversion, and visual question answering. If you would like to read the blog post that covers these concepts in more details, please check out the link in the description. These models differ primarily in their encoder and decoder architectures, which give them distinct capabilities for interpreting, processing, and translating across different textual or visual modality. Besides, to make this guide more interactive, I have designed a Streamlit web app to illustrate and compare outputs of these computer vision tasks and models. Feel free to explore this free web app as well as the code in our GitHub repository. Both links are available in the video description. Here is a quick peek of these outputs in a table format to display task name, output, runtime, model name, model type using the default model from the Hugging Face pipelines. Now we will dive into the details of 4 fundamental computer vision tasks. Firstly, let's start with image classification that assigns images into a predefined set of labels, which can be achieved by a basic vision transformer. Vision transformer or ViT serves as the cornerstone for many computer vision models later introduced in this video. It consistently outperforms CNN on image classification tasks through its encoder-only transformer architecture. It processes image inputs and outputs probability scores for candidate labels, well suited for the image classification task that only requires image understanding. The ViT architecture is composed of following components. Starting with image patching that breaks down input images into small, fixed-size patches of pixels, so that local features are preserved for downstream processing. This is similar to the tokenization step in natural language processing. Then convert image patches into numerical representations, also known as vector embeddings, so that images with similar features are projected as embeddings with closer proximity in the vector space. Extract and aggregate information from all image patches into one numeric representation called classification token, making it particularly effective for classification. Add position encoding to preserve the relative positions of the original image pixels. CLS token is always at position 0. Then use the transformer encoder to process the embeddings through layers of multi-headed attention and feed-forward networks, followed by a classification head to produce probability score of candidate labels. The mechanism behind ViT results in its efficiency in capturing global dependencies, whereas CNN primarily relies on local processing through convolutional kernels. On the other hand, ViT has the drawback of requiring a massive amount of training data, usually millions of images, to iteratively adjust model parameters in attention layers to achieve strong performance. Hugging Face pipeline significantly simplifies the implementation of image classification task by abstracting away the low-level image processing steps. We compare results of the baseline image classification model developed by Google by providing 2 similar images with different compositions. As we can see, this baseline model can be easily confused, producing significantly different outputs despite both images containing the same main object. Image segmentation is another common computer vision task that requires a vision-only model. The objective is similar to object detection but requires higher precision at the image pixel level, producing masks for object boundaries instead of drawing bounding boxes as required for object detection. DETR or detection transformer can be used as a baseline model to perform image segmentation. Although it is widely used for object detection, DETR can be extended to perform panoptic segmentation task by adding a segmentation mask head to assign each pixel an object class and an instance of that class. As shown in the diagram, it utilizes the encoder-decoder transformer architecture with a CNN backbone for feature map extraction. DETR model learns a set of object queries and it is trained to predict bounding boxes for these queries, followed by a mask prediction head to perform precise pixel-level segmentation. Mask-to-former is another common choice for image segmentation task. It is developed by Facebook AI Research and generally outperforms DETR models with better precision and computational efficiency. It is achieved by applying a mask detention mechanism instead of global cross-attention to focus specifically on foreground information and main objects in an image. We again used the Hugging Face pipeline to integrate DETR model fine-tuned on panoptic segmentation and display the output image masks. The model successfully identify and extract the cup and the dining table. The third type of computer vision task is image captioning, also known as image-to-text, translates images into text sequences that describe the image contents. This task requires capabilities of both image understanding and text generation, therefore well suited for a multimodal model that can process image and text data simultaneously. For example, visual encoder-decoder is a multimodal architecture that simply combines a vision model for image understanding with a pre-trained language model for text generation. A common example is ViLT GPT-2, the default model used in the Hugging Face image-to-text pipeline, chains together the vision transformer as the visual encoder and a GPT-2 model as the decoder to achieve autoregressive text generation. BLIP, on the other hand, is a standalone model architecture developed by Salesforce Research, leverages 4 core modules: an image encoder and a text encoder, followed by an image-grounded text encoder that fuses visual and textual features via attention mechanisms, and then an image-grounded text decoder for text sequence generation. The pre-training process involves minimizing image-text contrastive loss, image-text matching loss, and language modeling loss, to achieve the objectives of aligning the semantic relationship between visual information and text sequences. It offers higher flexibility in applications and can be applied for visual question answering too. Here we see the image captioning output if we choose a custom BLIP model by providing a Hugging Face model ID. Finally, let's talk about visual question answering, or VQA. This has become really popular lately because it lets users ask questions about images and get meaningful text answers back. Like image captioning, VQA needs a multimodal model that can pull important information from visual data while also being able to generate text responses within the context of the visual data. What makes VQA different from image captioning is that it takes user questions as input alongside the image. This means it needs to handle both types of input at the same time. Vision Language Transformer is a computationally efficient model architecture for executing VQA task. ViLT incorporates image patch embeddings and text embeddings into an unified transformer encoder. It is pre-trained for 3 objectives that are very similar to the BLIP model. Image-text matching aligns the semantic relationship between image-text pairs. Masked language modeling allows the model to learn to predict the masked word from the vocabulary based on the text and image input. Then word patch alignment learns the associations between words and image patches. ViLT adopts an encoder-only architecture with task-specific heads and with this minimal design reaches 10 times faster speed than a vision and language pre-training model. However, this simplified architecture results in suboptimal performance on complex tasks. For example, one drawback is that ViLT model produces token-based outputs for VQA rather than coherent sentences, very much like an image classification task with a large amount of candidate labels. In addition to ViLT model, BLIP model is a more extensive model that can be fine-tuned for performing visual question answering task and generates complete text sequences instead of tokens. When comparing ViLT and BLIP models for describing the coffee cup image, the outputs differ significantly due to their distinct model architectures. ViLT predicts the highest scoring tokens from its existing vocabulary, while BLIP generates more coherent and sensible results. Thanks for watching. If you find this video helpful, We have included more resources in the video description. Please like and subscribe for more upcoming videos. Look forward to see you in the next one.